All right, first problem. This one, a little, I don't want to say easier, a little more straightforward. Second problem, a little longer. Here we go. A compound that consists only of nitrogen and oxygen has a molar mass of 92.010 grams per mole and consists of 30.45% nitrogen. Determine the empirical and molecular formula of the compound. Very simple question. What is the empirical formula? What is the molecular formula? Now, when you're told to find those two things, you should know by now that you have to find the empirical formula first. Once you have that, you have to multiply by some whole number to arrive at the molecular formula. So just put that part out of your mind for now. Let's focus on the empirical formula. Let's write down what we know. So we're going to summarize the information given to us here. First of all, the compound consists only of nitrogen and oxygen. That is important. The compound has a molar mass, fancy M, of 92.010 grams per mole. And this is the molar mass of the actual molecular formula of the compound, okay? Next, we are told that it's 30.45% nitrogen. That's it. And we, from this information, have to figure out what is the empirical, what is the molecular formula. All right, well, if we know the compound only consists of nitrogen and oxygen, and we know that it's 30.45% nitrogen, then, since we know percentages added to 100, we can calculate from subtraction the percent oxygen in the sample. So my advice to you is don't try to map out in your mind, how am I going to go from this information to the final answer? Don't try to say, well, I'm going to do this and this and this and this and this, because it never works out in your mind the way you think it will, unless you're just like a superhuman calculator with an awesome memory. I'm not. So what I do is I look at what I'm given and I say, all right, I know I want the empirical formula. I know I'm going to need the moles of the elements to find that empirical formula. I don't know how I'm going to get there. But what I do know is that nitrogen and oxygen are the only elements in this compound, and I know the percentage of one of them. So I know I'm going to need to find the percentage of the other. And even though I don't know how to get to the end, I'm going to do that first. Then when I have that, I will determine the next step. Stop trying to map it out all the way to the end. All right? So what we can basically do is we can say that 100% is going to be equal to the 30.45% plus the percent of oxygen, because this is the nitrogen percentage, and then whatever is going to be the percentage of oxygen. So the percent of oxygen, if you take 100 minus 30.45, you're going to get 69.55% of oxygen. So now you can rephrase the problem and determine the next step. You have a compound with only two elements, nitrogen and oxygen. You have the percent oxygen and you have the percent nitrogen. How do I find the empirical formula? Okay, well, remember when we're given percentages, I need to figure out grams and then go from grams to moles, right? That's the way to do that. So, because when we talk about percentage, so many percent nitrogen, so many percent oxygen, it's the percentage of the mass. It's a percent mass that you're given, right? It's never the percent moles, it's percent mass. So you assume a 100-gram sample. You can assume any sample size you want, but what we're going to do is we're going to assume a 100-gram sample, right? And if it's a 100-gram sample, then that means in terms of nitrogen, there must be 30.45 grams of nitrogen in this sample, and there must be 69.55 grams of oxygen in the sample. Because we know the percent of the masses, and we are assuming a 100-gram sample just to make the math easier, so we don't have to do any actual multiplication. We know that these are the grams that are involved. So if I tell you, again, trying to determine the next step, this is how much nitrogen you have in grams, and this is how much oxygen in grams. How would you find the empirical formula? You would say, well, grams isn't going to cut it. I got to change to moles, and then find the mole ratios, and then write down the empirical formula. Okay, so I'm going to go calculate from grams going into moles. So I have 30.45 grams of nitrogen, and I have these two memorized. I know 1 mole of nitrogen is 14. I said I had them memorized, 14.007, the decimal gets me. I know it's around 14, and this is grams of nitrogen, cancel, cancel. And so if you take 30.45, divide by 14.007, you'll get 2.174 moles of nitrogen. That's the unit left over. All right, so I guess we'll do this in black as well. And then we'll take the oxygen, 69.55 0.55 grams of oxygen. Then, if we know that 1 mole of oxygen atoms is 15.999 grams of oxygen atoms, cancel. Then you take 69.55 divided by 15.999, you get 4.37, whoops, not 37, it's 347 moles of oxygen. Okay, then you ask yourself, well, now I know how many moles of nitrogen are in the compound and how many moles of oxygen are in the compound. Now I can calculate that empirical formula by doing the mole ratio. So start with nitrogen, I don't know why I put 0, sorry about that. 2.174 moles of nitrogen. I have to divide by something. I'm going to pick the smallest number, which in this case is the nitrogen. 2.174 moles of nitrogen. So we divide these out. You see it's a 1-to-1 ratio, so you get 1. That's the coefficient for the nitrogen. Then we do the oxygen. 4.347 moles of oxygen. We have to divide by the same number, so 2.174 moles of nitrogen. When we divide these guys together, we get something very close to the number 2. It's not exactly 2, but we can round it up to the number 2, and that's the subscript for the oxygen. So because we have the mole ratios, and we know it includes nitrogen and oxygen, we write the empirical formula as nitrogen subscript 1, oxygen subscript 2. Right? So NO2, that's the empirical formula. So you see it's a multi-step process. You know it's only 2 atoms. You know the percent of the nitrogen by mass. By subtraction, you get the percent of oxygen by mass. Then you assume there's a 100-gram sample. Then that allows you to say, well, okay, then if this were true, then it would be this many grams of each. Convert them each to moles, do the mole ratios, and then the problem is the same as before. Now we have to go to part 2. How do we go from the empirical formula to the molecular formula? And the empirical formula, you're going to multiply those subscripts by some number. All right, if the empirical and the molecular formula are exactly the same, then you're just multiplying by 1 and the subscripts don't change. Most of the time you're going to multiply by some other whole number. How do you figure out what that whole number is? You go back to the problem statement and you remember that the molar mass of the compound in question, not the empirical, the molecular formula is 92.010. So what we have to do is figure out what the molar mass of this empirical formula is, and then we can find the ratio of the masses. So we have to find the ratio of the masses. So we're going to figure out what the molar mass is of NO2. We have 1 nitrogen, 14.007. We have 2 oxygens, 15.999. And so NO2, when you take 14.007, 2 times 15.999, add them, 46.005 grams per mole. Now, the molecular formula is usually a larger number than the empirical formula. You want to figure out what the ratio is, the molar mass of the molecular formula, and you divide it by the molar mass of the empirical formula to get the ratio. Now, the molecular formula was given to us in the problem, the mass of it, 92.010. 92.010 grams per mole. And we just figured out the empirical formula is the mass of it, 46.005 grams per mole. Now the units completely cancel, so this is a dimensionless, unitless answer. It's just a ratio. But if you take 92.010, divide by 46.005, you get a number very close to 2. And that means that the mass of the molecular formula is exactly twice that of the mass of the empirical formula. So what this means is that if you have an empirical formula of NO2, right, then you can find the molecular formula by taking that empirical formula and just multiplying the subscripts by 2. So it becomes N2O4. You just multiply each of these guys down, and then the molecular formula is N2O4. Now, a more proper way to write it, I guess, is you would take that empirical formula, NO2, wrap it in parentheses, and put a little subscript of a 2 out there, and that forces the multiplication, which is N2O4. However you want to write this to show that you're multiplying is fine with me. You can do something like this, N2O4. So the empirical formula from experiments gives us the smallest whole number ratio of the atoms, of the moles of the atoms, okay? But the actual molecule, when you zoom in, it isn't actually 1 atom of nitrogen and 2 of oxygen. It's actually 2 atoms of nitrogen and 4 of oxygen because it's the same ratio of atoms in both cases, but the actual molecule is double the number of atoms from the empirical formula. All right, so now we have to turn our attention to our last problem. This problem, as I mentioned in the beginning, I wouldn't call it hard, but I would call it a nice multi-step problem that kind of stretches our mind to do things that we have done in the past and put a few different skills together. So let's read it. We're going to read it a couple of times, and we're going to talk about lots of little details as we go through it. It's called a combustion problem, finding the molecular formula when there's combustion involved, and you'll see how it's different from some other problems we've done. Here we go. A compound that consists only of carbon, hydrogen, and oxygen is analyzed by combustion. What I mean by analyzed is literally we burn it and we see what products form and we see if we can perform analysis of the original substance. Okay? The result of combusting 0.1650 grams of a sample produces 0.4030 grams of carbon dioxide and 0.1660 grams of water. So it produces carbon dioxide and water. All right? If the molar mass of the compound is 144.0 grams per mole, determine both the empirical and the molecular formula of the compound. So it's really the same problem as before. We want to figure out first what the empirical formula is, and then multiplying by some whole number, whatever that number is, figuring out what the molecular formula is. So that part of it's the same, but the difference is that this thing is combusted. In these other problems, we were just told, you have this going on in the compound, figure out what it is. Here, we're taking the compound and we're burning it. And notice that the products that you get from burning it is CO2, carbon dioxide, and H2O. And I told you, when we study combustion, we're going to study it more later also, but when we talked about combustion before, I told you that as long as there's enough oxygen available, you're pretty much always going to burn things and produce CO2 and H2O. We're going to learn later that when we burn things, those compounds always form because CO2 and H2O are very, very stable. They're just the lowest energy state. We're going to talk about energy later, but basically the most stable arrangement of those atoms is basically CO2 and H2O. And so it's very common when you burn things, as long as there's carbon and oxygen and hydrogen, you're pretty much always going to form carbon dioxide and water unless something else is going on. Like if you starve it of oxygen, maybe there's not enough oxygen to make CO2, then maybe you make carbon monoxide, CO, instead. But that's not what we're talking about here. So let's start by writing down what we have been given. And there's a lot of stuff. So what we're going to do is we're going to say the sample, this is what we're burning, is 0.1650 grams, okay? We don't know what it is, but it's some sample, right? And I guess I'll put an arrow here. I'll say burn or combust it. And then when we do that, what do we get? We get 0.4030 grams carbon dioxide. We know what that is, so I'll put CO2 instead of writing out carbon dioxide. And we also get 0.1660 grams of water, CO2 and H2O. All right. And what we also figured out is that the molar mass of the sample, or of whatever this original compound is, we're given is 144.0 grams per mole. This is all the information we have. We have burning going on, CO2 and H2O. So let's just try to understand how this might actually work. A compound consists of carbon, hydrogen, and oxygen. That means there needs to be some carbon, but I don't know how much of it, so I'm going to put X for the subscript. There needs to be some hydrogen, but I don't know what the subscript of that is, so I'm just going to put Y. And there needs to be some oxygen here, but I don't know what it is, so I'm just going to put Z. Right? And what I'm going to do is I'm going to burn it. That means I'm going to add oxygen to it, but oxygen doesn't exist by itself as just an atom. It's a diatomic molecule, O2, right? And this yields CO2 plus H2O, right? Let's make sure that what we wrote down represents what's in the problem. A compound contains only carbon, hydrogen, and oxygen. Check. Right? It's analyzed by combustion. Check. It produces so many grams of carbon dioxide, we're given that number right here, and so many grams of water, 0.1660 grams of water, H2O. And it only produces carbon dioxide and water. So the only thing weird about this is that I'm writing down a reaction, but I'm putting X's and Y's. Now, I'm not really going to solve this like an equation. I'm just trying to get it all on paper here so you can see what's happening. There's some unknown thing. I want to find out what this is. I want to figure out what X and Y and Z are. When I combine it with oxygen, I get this stuff. But notice something interesting. The sample, original sample, this thing, actually is only a mass of 0.165, right? But the carbon dioxide mass is 0.403 and the water is 0.166. If you add the masses of these together, you're going to get something bigger than 0.5 grams, almost 0.6 grams. But I only started with a sample that was much smaller than that. Doesn't that violate conservation of mass? I start with something, only has 0.16 grams, but when the products that form have more mass. How is that possible? But then you realize, well, wait a minute. This is the mass of this. What must be happening is it's taking oxygen from the air. So there is oxygen in this compound. True, some of this oxygen does go into this. That's true. But it takes additional oxygen from the air and goes into the rearranging. And so the extra mass is coming from the oxygen in the air. Because remember, oxygen is 15.999 grams per mole. Oxygen floats around. We think it floats around, but it has mass. And so the mass of the products is coming from the mass of the starting sample, but also from sucking in extra oxygen from the air. So it's not surprising that the mass of the products would be bigger than the original sample when you burn something, right? That's one very important thing. All right, now we cannot map a strategy to get all the way to the end here, but we know that to figure out the empirical formula, what we need to do is know the moles, the number of moles of the carbon, the hydrogen, and the oxygen. But we're not given any moles. Instead, what we're doing, what we have been given, is the mass of the sample, the mass of the carbon dioxide produced, and the mass of the water that is also produced. All right, my advice here is the oxygen is problematic. It's difficult to figure out what's going on with the oxygen because the oxygen is also coming out of the air. So don't focus on the oxygen at first. You know, when we balance chemical reactions, I gave you the advice, save oxygen for the end because it's a little weird because it's off by itself and it can exist in multiple different compounds. Leave it for the end. Same thing here. We need the moles of the carbon, hydrogen, and the oxygen. Just ignore the oxygen for now. Let's see if we can figure out the number of moles of the other parts of this problem. And what we know is that there's 0.4030 grams of carbon dioxide produced, and we know how many grams of water produced. What we want to do is figure out what is the molar mass of these two things because we want to convert to moles at some point. So let's go ahead and figure out what the molar mass of carbon dioxide is. We know we're going to need it at some point. We know carbon is 12.011 grams per mole. Oxygen is 2 times 15.999 grams per mole. So if we take the 2 times 15.999 and add this guy, what we're going to get is 44.009 grams per mole. That's the molar mass of carbon dioxide. We're going to do the same thing for water, right? We know there are 2 atoms of hydrogen, 1.008 grams per mole, 1 atom of oxygen, 15.999 there. So we multiply this, we add the 15.999, we get the 18.015 grams per mole. If you don't know what to do in a problem, it's a pretty good idea to take any compounds that you have and just find their molar mass because you're probably going to need it at some point. And if you don't need it, then it just sits there, but you probably will need it. So we do that first. We know how many grams per mole in each of these cases. Now we know how many grams of carbon dioxide, is actually produced. So we write that down, 0.4030 grams of CO2. This is how much grams of CO2 is produced. But we now know the molar mass of CO2, so we can calculate the number of moles of CO2. We know that 1 mole of CO2 has a mass of 44.009 grams of CO2. Cancel, cancel. So if we do this calculation, we're going to get the number of moles of carbon dioxide. That's awesome. But notice what we really need. We don't really need to know the number. We want the mole ratio. We want the moles. But we really don't want the moles of carbon dioxide and water. We really want to know is how many moles of carbon and hydrogen and oxygen were in the original sample. We have to have those moles. If we stop the calculation here, we know how many moles of carbon dioxide were actually produced. But notice that all of the carbon in the products is in here. So if we can figure out how much carbon is in this, carbon dioxide, then that is the same amount of carbon that existed in the original sample, which is what we want. How many moles are here? So how can we figure out the number of moles of carbon here? We have the moles of CO2, but we also know that 1 mole of CO2, because the formula is CO2, there must be 1 mole of carbon in 1 mole of CO2. Because if I have 6.02 times 10 to the 23rd molecules of this, and I break it apart, I still have that many atoms of the carbon. The moles of CO2 cancel with the moles of CO2. All right? So if I take 0.4030 grams, or 0.4030 divided by 44.009 times 1 divided by 1, which doesn't really do anything, then what I actually get is 0.009157, and this is moles of carbon. Now, what you've calculated here, you know the grams of the carbon dioxide, you know the molar mass of carbon dioxide, and you know how many moles of carbon is in a mole of carbon dioxide. So what you calculate here is the number of moles of carbon in the product. But since you know that the product, the only carbon in the product has to come from here, then you know that the moles of carbon you find here has to be the moles of carbon that's present in the original sample. You know that because you know that it produced CO2 and H2O. And so we found the number of moles of carbon in the original sample. We want to find the mole ratios. We have to know the number of moles. Now we found the number of moles of carbon. Okay, so let's do the same thing for the other thing that we can do, which is hydrogen. We now know how much water is produced. 0.1660 grams of H2O. We now know the molar mass of H2O. 1 mole of H2O, we just calculated 18.015. So we put 18.015 grams H2O. All right, grams of water cancels with grams of water. If you stop the calculation now, then you figured out how many moles of water are in the product. But we also know that 1 mole of H2O contains, because there's H2 here, 2 moles of hydrogen. For every 1 mole of this unit, break it apart, there has to be 2 moles of hydrogen. Cancel, cancel. So if we stop the calculation now, how many moles of hydrogen do we have? If you take 0.1660 divided by 18.015 times 2 divided by 1, you get 0.01843. 0.01843, and this is moles of hydrogen. So now we're getting close to the answer because we want to know how many moles of carbon are in the original situation. We figured that out by figuring out how many moles of carbon were in this, and that has to be the same as this. Now we know how many moles of hydrogen were produced because of the water that was given to us, and we know that because the hydrogen only exists here and here, this amount of hydrogen, which is this many moles, has to be the number of moles present in the original problem. So we now know the moles of the hydrogen and we know the moles of the carbon. So now we save the best for last because it's a little trickier. The oxygen's a little different because there is oxygen here, it's true, but we're adding oxygen here and then the oxygen is actually present in both of these products. So it's a little harder to figure out what the number of moles of the oxygen is. So we have to take it one step of the time. Okay? What we really want to know is we know how many moles of carbon are in this. And we know how many moles of hydrogen are in here. Notice one other piece of information given to us, the sample. We know the mass of the sample. If we know the moles of carbon here, we can turn that into grams. If we know the moles of hydrogen are here, we can turn that into grams. If we know how many grams these two comprise of, or we know how many grams these two things are, then by subtraction, because we know the mass of the sample, which is the whole thing, we can figure out the grams of the oxygen. And that's what we need. We need to know how much oxygen is in the original sample. We now know how much carbon and hydrogen is there, but unfortunately that's moles. We need to turn them back into grams, which is a little bit of a pain. I mean, I agree with you, it is a pain. I told you it was going to be a multi-step problem. So let's start out with this one, with the carbon. 0.009157 moles of carbon. All right, but we know that 1 mole of carbon is 12.011 grams of carbon. Cancel, cancel. So what we can do is take the 0.009157 and then multiply by 12.011, and what we get is 0.1100 grams of carbon. This is in the original sample. I'll put original sample. Right? Now let's do the whole thing again. So what we have here for the hydrogen is 0.01843 moles of hydrogen. We're going to convert that back into grams, right? So what we know is that 1 mole of hydrogen is 1.008 grams of hydrogen. Cancel, cancel. All right? And so if we take 0.01843 and we multiply by 1.008, what we get is 0.01858 grams of hydrogen in the original sample. So this is the grams of carbon that are in here and then here, but this amount of carbon in here and here is the same as the amount of carbon in here and here. So essentially what we figured out is we know the grams of this and the grams of this, and we know the grams of the entire thing. So by subtraction, we can figure out what this is. So let me write that subtraction bit here at the bottom. Let's figure out what the grams of oxygen is. What we can say is that the original sample, 0.1650 grams, I'm going to put under here, this is the sample, right? That's equal to the mass of the carbon. The mass of the carbon is right here, 0.1100 grams. This is carbon. And then you add to that the hydrogen, 0.01858. This is the hydrogen, right? 0.185, just double checking I'm writing everything down correctly. And then you're going to add to that, I'm just going to put oxygen in gram. I guess I'll just put oxygen. I guess I'll put oxygen mass, right? So we know the total sample mass. We know the amount of grams of carbon in that sample, and we know the grams of hydrogen in that sample. So we add these two things together, and then we take this number, subtract, once we've added them together, subtracted that back, and then what we get is the mass of oxygen, when we do that subtraction, is 0.0364 grams of oxygen, 0.364. So now we know the grams of this, the grams of this, we know the grams of that oxygen. We know how to turn grams of anything into moles. Moles is what we need. So we start with the 0.0364 grams of oxygen. 0.0364 grams of oxygen. How do we go into moles? We say that 1 mole of oxygen is 15.999 grams of oxygen. Cancel, cancel. So if we take 0.0364, divide by 15.999, you get 0.0028, whoops, not 28, 228 moles of oxygen. 0.00228 moles of oxygen. Okay, let's stop for a second. We want to find the empirical formula of anything. How do you do it? If you have an unknown substance, you must know how many moles of each of the elements that are in there. Once you have the moles of each of those species, then you can figure out the mole ratio and you can figure out the empirical formula. We now know how many moles of oxygen are in this sample. We know how many moles of hydrogen are in this sample, and we know how many moles of carbon are in that sample. So we can actually find, finally, the empirical formula. The smallest of these numbers, I believe, is going to be the moles of the oxygen, right? Because 0.0022 is the smallest between this and this. So what we're going to do is I'm going to write down the moles of carbon, write down the moles of hydrogen. We're going to divide by the smallest of them, which is the moles of the oxygen. So from the previous page, I'm just going to write down the number of moles of the carbon, 0.009157 moles of carbon. 009157, that's the number right here. And we're going to divide that by the smallest number, 0.00228 moles of oxygen. All right, so we take these two numbers and divide them. We get 4.02, which is close enough to 4. And this is going to be the subscript for the carbon. All right, next we're going to take the hydrogen, 0.01843. So 0.01843 moles of hydrogen. We're going to divide by the oxygen, 0.00228 moles of oxygen. When we take 0.01843 divided by 0.00228, we get 8.08. and that's close enough to 8 within experimental error. The reason we're getting these decimals is because it's experimental error. And then finally, we have the moles of oxygen we're going to divide by itself. So just for completeness, 0.00228 moles of oxygen, we're going to divide by itself, 0.00228 moles of oxygen, and you get 1, and that's for the oxygen. All right, finally, drum roll please. We take all of these numbers, and we know that carbon has a subscript of 4, right? Just double check myself. Carbon has a subscript of 4. Hydrogen has a subscript of 8. And oxygen has a subscript of 1. So this is the empirical formula of this whole thing. All right, a lot of work. We're going to review it at the end. Okay, so just take a deep breath with me. We now have the empirical formula. How do we go from empirical to molecular formula? Well, we have to have some additional information. And in this problem, we are also told, we've given all the grams of the sample, but we're also told the molar mass of the actual molecule, 144 grams per mole. But now we know what the empirical formula is. It's this. So let's figure out what the molar mass of this thing is and then take the ratio of it. So the molar mass of C4H8O, what is it? It's 4 carbons, 4 times 12.011. My marker died there, so I'm going to throw that away. We have 8 oxygens, 1.008. And we have 8 hydrogens. Sorry, I said the wrong thing there. And then 1 oxygen, 15.999. So the molar mass of C4H8O, when you multiply and add all these guys together, you get a molar mass of 72.107 grams per mole. Right? So to figure out how to get the molecular formula, we need to take the ratio of the molar mass of the molecular formula and divide by the molar mass of the empirical formula, because they might be the same, but in this case we can see that they're different. So the molecular formula, if you go back to the original problem, had a mass of 144.0 grams per mole. So 144.0 grams per mole. And the empirical formula we just figured out has a molar mass of 72.107 grams per mole. Now the units cancel because it's dimensionless, and when you do that division, you get something very close to the number 2. So what does this mean? It means the molecular formula is basically exactly double the mass of the empirical formula, so the multiplier is going to be multiplying times 2. So the empirical formula is C4H8O. And one easy way to multiply by 2, you just take that empirical formula, wrap it in parentheses, put a 2 out here. This forces us to multiply each of them by the number 2. So it would be C8H16O2. C8H16O2. And this is the molecular formula right here. This is the final answer of this. So the empirical formula, the molecular formula in this case are different. Notice the ratio of each of these, like 8 to 2. There's 4 times as much carbon as oxygen. Well, in the empirical formula, there's 4 times as much carbon as oxygen. The ratios of everything are the same, but the actual molecule has more atoms in it bound together in a unit like this. Now, I'm not going to lie to you. This problem is tricky, and we could do another one like it. You know, it just depends. Are you going to have to solve a lot of problems like this or not? I don't know. Maybe we could do more, but I kind of think the point has been made here. Nothing in this problem, though, nothing is really new. It's just a matter of, like a lot of times in science, math, physics, chemistry, you have to practice. It's like, you know how to play basketball or soccer. I mean, everybody knows the rules, but you have to practice it, because getting the muscle memory of knowing what to do and getting experience, that's what it is. I mean, I know how to play the violin. I tinker with the violin, but I'm not good at it because I haven't put in 10,000 hours of training myself what to do. So everything in here has been stuff we've done, but you may be looking at this saying, I would never figure this out. Well, I'm telling you right now that if you're telling yourself that, then maybe what you're really saying is that you can't map out from start to finish the exact path from start to finish in your brain before you get started. I can't do that either. But what I do then is I try to take it one step at a time. When we're trying to find the empirical formula, you have to have the number of moles of the different elements in that formula. You have to get there. So you have to get a path just to find the number of moles in the original sample. So then we go back to our original spot here. And we write down a little reaction to help us visualize what we're doing. The original compound had carbon, hydrogen, and oxygen. You add more oxygen to it, break things and rearrange it, and this is what you get, right? We find the molar mass of these things because, in all honesty, you're almost always going to need it. So just do it. So here we have that. Even if you don't know what to do, just do that, okay? Then you say, well, they gave me the grams of everything, so I must need that for something. I put the grams of CO2 down. All right, now I have the molar mass. I can go from grams to moles. Why am I doing that? Because I know I want moles in the end. I have to have the moles of whatever. But the problem is if I stop here, I have the moles of carbon dioxide. That's not what I want. But then I know, well, in 1 mole of CO2, there's 1 mole of carbon. Bingo, that's the amount of carbon in moles in the carbon dioxide. But because I wrote the reaction down, this amount of carbon must be the same as this amount of carbon. So now I found the number of moles of carbon. I do the same thing for the hydrogen. This is how much water I have. Molar mass of water gives me moles of water, but then for every 1 mole of water, there's 2 moles of hydrogen. Boom, I have the moles of hydrogen that exist right here, but that must be the same number of moles that are present here because there is no more hydrogen anywhere in this reaction, in this equation. Oxygen is the tricky one because you start with it in here and then you add more to it. So you probably start trying to subtract things and just trying to get it easy, but then you realize that none of that stuff is going to work. What you really have to do is you say, all right, we're given the mass of the original sample. We now know how many moles of carbon and hydrogen are here, so we convert them. Moles of carbon, grams of carbon. Moles of hydrogen, grams of hydrogen. Now I know how many grams of carbon and hydrogen are here, which means they must be the same grams here. And I know the total mass here. So by subtraction, I know the total mass, grams of carbon, grams of hydrogen. By subtraction, I get the mass of the oxygen. That is the critical key point. The subtraction, depending on what you're given, to figure out the unknown, which was the oxygen in this original sample. Now I know the grams of the oxygen. Okay? So then once I know the grams of the oxygen, again, I convert grams to moles. I know now the moles of oxygen along with the moles of the other 2 species. I do the mole ratios like always. I get the empirical formula. All right, now I take this empirical formula here and I find the molar mass of it. Why? Because I was given the molar mass of the molecular formula. By knowing both, I take the ratio of both of them. The multiplicative factor is 2. Take the empirical formula, multiply by 2, and then that is the answer. Now, is it tricky? Yes, it's tricky, but nothing in here is different. We know how to find grams from moles and moles from grams. We know how to find the empirical formula once we know the moles. We know how to do all the calculations to get the moles. We know how to the conservation of mass, so we know we can subtract things and add things if we know that the total mass must remain unchanged, right? Which is what we use when we subtracted to figure out the grams of the oxygen there. And then we also know how to do the multiply the subscripts to get the molecular formula. So none of it was really new, but it was stringing a whole bunch of stuff together. My advice, if you still don't totally get it, watch it a few times and then get your own pencil out, write the problem down and do it yourself. You have to go through the mental gymnastics of how to get there and practice it. Just like running or jumping or track or field or basketball or baseball or golf, you have to practice it. So please practice this. Follow me on to the next lesson. We'll continue your skills in chemistry. Learn anything at mathandscience.com.